Hello, everyone. You're joining us for Improving Production Economics in Photonics Test and Assembly and Ultrafast Laser Materials Processing of Transparent Materials. This webinar is presented by PI, Physik Instrumenta, and hosted by Photonics Media. I'm Sarah Weiler. I'm the webinar coordinator with Photonics Media. You'll be hearing in this next hour from two presenters. The first is Scott Jordan, head of Photonics for PI and a PI fellow. Over the course of his career, Jordan has made multiple contributions to photonics alignment automation and precision motion control and optimization technologies. You'll also be hearing from Matt Price, technical manager for PI, working in precision automation technologies for microfabrication and metrology, who works to develop motion technologies in laser materials processing and characterization. Our presenters today will be discussing the latest advancements in precision motion control techniques, system architecture, software, algorithms, hardware, and mechanisms for system designers in the laser processing, optics, and photonics industries. If you have any technical issues during the webinar, please log out and log back in to rejoin. But if that doesn't fix it, a recording of today's webinar will be available on the Photonics Media website shortly after today's presentation. So if you need to revisit any material or share it with a colleague, you will be able to do that very easily. And you'll get those links in your email inbox just about in a day or two. There's going to be a Q&A at the end of today's presentation, but you can ask your question at any time or leave a comment for us in the chat, and we will respond to you either today at the Q&A or afterward by email. So with nothing further from me, I'd like to introduce our first speaker, Mr. Scott Jordan. Welcome, Scott.
Thank you very much, Sarah. I need to show my PowerPoint window. So yeah, the theme for our talk today, at least for the photonics segment, but also for Matt's segment, is improving production economics in photonics test and assembly. So let me say a little bit about that topic. First, these are early days in the photonics industry. Here is a video of an early fab back in the 1980s. This is Intel's fab, and chances are good your first IBM PC's brain was manufactured in this facility that you see here. It looks quite a bit different from today's fabs because those tool makers that we are so familiar with today, ASML, Tokyo Electron, Lam Research, KLA, those big guys, they didn't exist back then, or they were just getting started. So today, they exist. You can build a new fab from the ground up just by writing purchase orders. In photonics, it's not so simple. Now, a little bit about us. We are a global company that specializes in ultra precision positioning, such as the alignment process required for assembling and testing photonic devices. As you can see here, we span the globe. We have manufacturing, engineering, consultation, training, service support over the entire world. And we have been doing automated alignment for a very long time. We have actually well over 100 man-years of alignment expertise by now in our global organization. And alignment, as you will see in my slides, is the most painful part of producing and testing the photonic devices today. There are basically two paths that customers can take, device makers. The first is the early semicon model, similar to that slide that I just showed you with the video in it, filled with custom equipment and manual processes. Now, this can involve engaging local or captive integrator teams to build custom machinery, and that's a very valid approach. And perhaps the majority of our customers choose this approach to build their own equipment because that ecosystem is just starting to emerge. Now, today we have that ecosystem is just a few players, but they're doing a spectacular job. One is Form Factory, for example, makes wafer probers to test the devices before they go to production, packaging and assembly, things of that sort. Since the costs are in the packaging, you need to be sure that the device is healthy before it proceeds into further production steps. So that's why wafer probing is so very important for photonics today. At the other end of the production spectrum, there is Tegema. Takema has recently come up with a very new class of tool that utilizes the parallel capabilities of our alignment technology in a spectacular fashion. And that makes their tools 10 times faster than those built on legacy equipment. So we'll talk a little bit about them. Now, our role is to provide the motion hardware. Our legacy is in piezoelectric devices where we have, let me call up a laser pointer here, where we make our own piezo ceramics, for example, and we build them into assemblies of really high precision positioning equipment, positioning sensors and controls and things of that sort. Over the years, we have grown into larger and larger devices, larger form factors of motion. And we have acquired ACS, which is a very well respected manufacturer of industrial class controls. So this has allowed us to flexibly serve our marketplace with lots of potential implementations to suit people's needs. Now, for photonics, we're here today because of our appetite for data. And one of those applications that consumes so much data these days, I don't think any of us saw it coming, and that's taking selfies. Here's some statistics, some amazing statistics from 2016, where a single selfie-related application on the internet, Google Photos, 24 billion selfies, 24 billion selfies. That's just a subset of the number of photographs were uploaded to Google Photos in 2016, 5 years ago. I'm sure the number is higher today. It doesn't include any of the other applications that also serve the selfie market, shall we say. Instagram, Facebook, Snapchat, WeChat, Apple iCloud. This enormous amount of data is being traded just from people taking pictures of themselves. Nobody saw that coming. And in addition to that, we have smart vehicles, we have Internet of Things, we have personal medicine, we have genomics, so many applications generating so much data that is what is driving the photonics industry. So almost all that data goes to the cloud and gets transferred from place to place. So that's just one application. Throughout the manufacturing of photonic devices of all sorts, the alignment process must be performed. Unlike microelectronics, where the positioning is good enough if you're within maybe 20 microns of a pad, and you can make a connection effectively with that kind of precision. With photonics, it's about 1,000 times more sensitive. So you can't just do it with a camera. You can't just do it with fixturing. You might be able to do it with V-grooves and other passive alignment techniques, but then again, those V-grooves and other passive alignment techniques must be manufactured to commensurate tolerances, which isn't cheap. So for the moment, alignment is a repetitive cost that begins at the wafer level and repeats typically a couple dozen times throughout the production chain. And this has been recognized in multiple studies. Here's one from 2017 from Cadence. Here's one from 2006 and Journal of Lightwave Technologies. And they all say the same thing. Alignment is painful. So what we have tried to do is make it less painful by integrating a new kind of alignment technology into our motion controls, into our devices themselves. So you just issue command and it achieves the necessary alignment automatically and very rapidly. So the way we do this is what I will explain in the subsequent slides. But what you need to know is that this is a generic capability that we have spread across multiple types of motion equipment, from our classical nano positioners, which are extremely fast and take you down into the nanometer scale in terms of precision, to our hexapod microrobots that give you all 6 degrees of freedom and the ability to perform rotations about any point in space, to our large format stages, the big linear motor stages, gantries, things of that sort. These are all mechanisms that can now benefit from this alignment automation technology. Okay, so the basic challenge is to find the best peak of some figure of merit, typically optical power, but it could be other things as well. Find the best one, select that one, grab onto that peak, lock onto it so that if drift occurs due to curing stresses in the glues that are used to assemble devices, or just from heating up, just from thermal effects, to be able to track that in multiple degrees of freedom. And today's devices have multiple channels. They have multiple inputs, multiple outputs, and they may not present a nice, clean Gaussian figure, a nice Gaussian shape. So you can't make that assumption with today's devices, which means that an alignment technology suitable for silicon photonics and beyond must be able to accommodate asymmetric and non-circular and non-Gaussian sorts of couplings. So that's part of what we have done. Plus, these devices are today, almost all of them are multi-channel. So we need to be able to align multiple channels at once. In this animation, we show just 4, but I'm working with 16. I work with up to 96 channels per device that need to be aligned, and there's multiple degrees of freedom to do that. Compared to previous alignment techniques that require a looping, repetitive alignment process, this is about 99% faster. So it's not just a small improvement. It's a dramatic change, and that's because it's dramatically new technology. So let's talk about that. I mentioned that built into our controllers are alignment functionalities, key functionalities, such as an area scan, which is, in this case, in this slow motion view, it gives you the idea. It's a sinusoidal, either a rectangular format scan or a spiral scan. But the key is it's a single frequency. You can choose the frequency. You can choose a frequency that does not cause resonances in your system so that there's no settling time. By eliminating settling time, you make everything faster. And then you'll notice that we scanned over the whole area. We were able to localize that peak pretty well, even though it lies between the scan lines. That means you can use a fast, coarse scan and still localize the best peak very well. So this technology is built into our controllers. It's a command that allows you to rapidly characterize a coupling in whatever degrees of freedom and find the peak. Now, that was slow motion view. The actual speed is typically around 300, 400 milliseconds. So it's very fast and very useful for that reason, because it's a command. The computer doesn't have to tell it to go from point to point to build up that scan. It happens automatically. Now, the second type of scan is what's called a gradient search, where we perform a small circular motion of one device with respect to the other. And that causes a modulation of the optical figure of merit, optical power, whatever, the coupling. And our controllers observe that and automatically climb the mountain to achieve and track the optimum. And the benefit of this approach, the way we have implemented, what's completely new, is the ability to do what you just see on the screen here in multiple degrees of freedom across multiple inputs and multiple outputs and multiple elements simultaneously in parallel. So we take this very long, painful looping approach that former technologies required and can take minutes to achieve, and we've reduced it down to typically 300, 400 milliseconds. So then followed by real-time tracking. Now, that again was a slow motion view. The actual time, as I mentioned, is typically about 300 milliseconds. And then you can have it stop at the optimum or continue to track if you might have drift issues for whatever reason. Now, how it works. Let me call up my laser pointer here. Here you have a figure of merit. And in this case, it's optical power, typically something like a Gaussian, but it's hill-shaped. What we do, doesn't have to be a Gaussian, it does need to have a peak. What we do is we perform a small circular motion of one device with respect to the other. And notice at this point, we have this much figure of merit, this much coupling. At this point, we have this much figure of merit, this much coupling. So as we go around and around, you get this quasi-sinusoidal modulation of the optical figure of merit, the coupling, the power, whatever it is you are trying to optimize. It could be many different things, but the controller will automatically see that modulation. And from its amplitude and phase, it's able to say which way to go. to achieve optimum. So what's new is this ability to do this simultaneously across multiple degrees of freedom, multiple inputs, outputs, multiple elements, all doing that all in once. So that's what I will show you in some videos later. Now, as I mentioned, the metrology, the figure of merit, it can be many different things. For photonics devices, it's typically optical power. People want to optimize the throughput of their devices, but it could be polarization. It could be some measure of wavelength. It could be some calculation, such as image quality in a camera assembly, where you might want to optimize the contrast or the modulation transfer function or a 2D Fourier transform or something of the sort. As long as it's fast, because our system is fast, as long as your figure of merit is fast, it's high bandwidth, we can use it to optimize whatever it is, whatever assembly you might want to optimize. So that means things like laser cavities, things like lens assemblies for imaging lenses. These are all something that can be really improved in terms of production economics using this technology. So let's talk more about that parallelism aspect. This is the old way of doing things. This is a single process that was slow, single alignment. This is what I'm talking about. Multiple fast processes running in parallel. You can imagine the difference in productivity between these two paradigms of operation. So let's consider an array device. This is a very cool one using some technology from a brilliant company in New Jersey called Photonics. This is a pitch reduced optical fiber array profile device. More than 90 channels are possible, very, very accurately spaced, very compressed, so they take up very little silicon real estate. So this particular one, you can see the chip right here that they're coupling to, and this is their fiber probe array with its 60 or 90 channels. And the way you would align this or any other array device is conventionally you would do the following. You would align an X and Y, and then you would make a small theta Z motion. And even if you're using a hexapod and can place the physical rotation axis anywhere in space with a single software command, even then, chances are excellent it's not going to be exactly to the nanometer on the optical axis. So what that means is that when you make a small theta Z motion, you de-align an X and Y. So you have to stop and go back, realign X and Y, and then repeat that process in a big painful loop that can take several minutes to achieve. Or you can do the PI parallel way and do it all in one step. So here's an example. We showed this for the first time at Photonics West 4 years ago. We showed some single mode fiber glass arrays, and we brought them close together using a hexapod and a nanocube. And then we had some software. It ran all week, and this is what it did. First, we would do an area scan that would allow us to localize the main mode of one of the channels. And then we would do a parallel gradient search alignment in theta Z to optimize in theta Z. So the job's done. We optimize in XY with a continuous parallel gradient search in X and Y. And then we did theta Z to align the whole array in theta Z so that now X and Y is aligned, theta Z is aligned, and we did that in one step. Now, the next year, we did this with a device that has array inputs and outputs. So again, we do an area scan on both sides. We do a gradient search lock on both sides. We do a theta Z alignment on both sides, and we're done. So the interesting thing about this video is that there's about twice as many alignments. There are twice as many alignments as in the first video, but it takes about the same amount of time. And that's because everything is being done in parallel. With this technology, the overall time to align is almost independent of the number of alignments being performed because they're being done in parallel. Pretty amazing. So this has been utilized by several OEMs and many academic and other researchers and in-house integrators. One of the first OEMs was FormFactor. It makes wafer probers, engineering probers they're called, and they have this wonderful video that I recommend highly. This is just an excerpt. It's on YouTube, and it's really very informative. It talks about the whole process of probing photonic wafers, and I highly recommend it. But you can see they're talking about doing your tests of thousands of devices on the wafers in a few days rather than months or years because of the faster alignment and because of all the efficiencies that allows them to build into their tools. So here you can see they're talking about the ability of the hexapod to rotate about any point in space, and then add that to the fast alignments and the raw capabilities of their tools, and you have very, very successful product. So the wafer level probing, this is now the industry standard for photonics wafer probing, and it's really, really very, very good to see, because wafer probing, as I mentioned, is really important for the economics of producing photonic devices. Another example. Oh, well, this is actually more form factor. This shows you some of their edge coupling devices. Remember I said earlier, this is a generic alignment process, alignment capability. It can be used for edge coupling, for diffractive coupling, for laser cavities, for lenses. It doesn't matter. If you need to optimize some sort of a signal, that's what this does. Okay, now, form factor prober was also featured in some press releases and announcements. A very interesting quantum computing company in Silicon Valley called PsiQuantum. There's a wafer prober probing quantum wafers, and that's interesting because remember, wafer probing is what you do when you are getting into manufacturing. So when I see a quantum computing company doing wafer probing, you can be sure things are happening, things are getting close. This is not technology our grandchildren will maybe see. This is something that is imminent. Very exciting stuff. Highly recommend you read up on them and see what they're doing, and there are plenty other companies out there doing really interesting things. At the other end of the production chain is assembly. Once the device has been validated at the wafer level, it gets diced off the wafer level, diced off the wafer, and proceeds to packaging, attachment of fibers, inputs, outputs, electrical, other provisions. So that whole process can be done manually, but to keep up with the competition and to improve production economics, it needs to be automated. Tegema has taken the technology I've described and they've put it together into a flexible tool assembly that can be extended to full robotic assembly, whatever the customer might want to do. And it's 10 times faster than legacy technologies. Large format applications, my colleague Matt, who will speak next, has been very intimately involved in taking the same technologies we've described and bringing it to our industrial controls made by ACS. This allows us, for example, to cover inspection of circuit boards that might have emitters sprinkled all over them. You may have devices that are several centimeters. You may have trays that are many centimeters big, and you need to probe each one of them over a large area. And that's what this allows us to do. So this technology is something that we believe is a real enabler for these larger assemblies and larger carriers and trays and coupons and things of that sort that are bigger than your typical singulated device. Very exciting. Now, we've even shown this at trade shows. For example, this was at the last big laser show before the pandemic hit. We took an assembly with big linear motor stages, gantries, hexapods, nanocubes. We put it all together We put it all together to perform in this case, a simulated alignment. The devices were real. The devices and the alignments were real, and they were live. We were not showing customer devices. We made them out of glass fiber arrays, and you can see here, large travels moving, doing parallel processing between 3 different nests, showing how pick and place can happen at the same time as alignment on a different nest. And that was a very, very effective demonstration of how this technology can be scaled into a very highly customized configuration. And then at the other end of the scale, if you've never seen an atom before, now is your chance, because this is some brilliant work that was being done at Purdue University's Burke Nanotechnology Center, and now at the University of Illinois as well. Scanning, characterization, alignment, and tracking of single photon emitters, atomic scale defects in diamond. What's known as nitrogen vacancy centers. They fluoresce. They're basically atomic scale emitters. And so what we did, it took about, took a day to make starting from a blank screen, to use the software stack that PI provides to build this workstation. This blue box is an area scan, and a very fine area scan over a rather large area, but we were able to determine where the emitters existed on a microscope slide covered with diamond. And each of these little blobs, each of these little white areas is an atom emitting. And the way we made the workstation, if there's an emitter of interest, you can click on it with the mouse and the system will lock onto it and perform tracking if it should move around for thermal reasons or whatever. So that's an example at the other end of the device spectrum. Sometimes customers ask, how scalable is this? How far down can you go? There you have your answer. In imaging lenses, we do something similar. That very brief animation that just showed you multiple lenses being aligned simultaneously to optimize. In this case, a figure of merit is typically a calculation of image quality, something like the modulation transfer function or a 2D Fourier transform. And this allows us to perform multiple alignments of multiple lenses and multiple degrees of freedom simultaneously. Free space optical communications is another place where we are seeing some adoption of our devices, and who knows, perhaps this alignment technology as well, because among the many things we make are very, very fast beam steering devices, including space qualified ones. And so these will shortly be directing communications from satellite to satellite in these immense global networks that are being established by several players. So this is something that we can do. We actually have a blog post that I recommend. You read about the fast steering mirrors for these deep space applications and terrestrial as well. In a way, this brings the photonics industry full circle, because the first big photonics boom in the late 1990s was to eliminate the dependency on satellites for communications. In that case, it was long-haul telecommunications. But today, here we are again, using satellites to enable global telecommunications with really high speeds this time, because these are not geostationary satellites, they're much closer. So the lags that existed with geostationary satellites don't occur. And that takes me to my last slide. Please feel free to get in touch. I hope that we can help you improve the economics of your photonics production and test.
Hello. Let me thank Scott for his nice presentation. And I'll preface my talk, which is really on laser materials processing of transparent materials, with this epiphany I had listening to Scott's talk. And that epiphany was, curious enough, he talks about the data related to selfies. And I'll be talking a little bit about the materials involved in taking selfies, camera covers and display technologies. And so my thought is the title of our talk could have easily been How PI is Improving Your Selfies. So That was my thinking. So anyway, I'll step through. PI, as you can probably tell from Scott's talk, is supporting a lot of different customers at the leading edge of their different technologies, serving a lot of end markets, doing a lot of interesting things with precision automation. Here's a slide of some of those end markets we're serving. And really, my talk specifically could probably, in theory, be part of all of these. So really, generally speaking, the topic of my talk is how we go from a laser and a material that gets matched for a particular outcome function of the material to making that into a tool, and then why transparent media is particularly of interest, and then giving a few examples of particular motion approaches, which I think are less common than laser materials approaches, onto how you get a desired effect in the material. With the laser and the motion system sort of working synchronously, for lack of a better word. So, and then we'll have some Q&A at the end. So to start, sort of for anyone that's done this, this is how I started my career as a laser apps engineer in a lab, trying to make a laser work with the material to the best desired effect in terms of resolution, function, performance. And this is where the journey starts, I think, for anyone that considers this. I've got my material, I want to do X, and now I want to couple it to a laser and have it perform this way. And so that's a good place to start. Picking the laser, picking the recipe, wavelength, rep rate, pulse width, these things go into a process that then gets brought to the motion system. And now the motion system is wrapped around that process to give you the best desired effect in the material. And one thing that we've seen directly is a laser materials process may have the best possible effect with that laser, but be limited by the motion system that's used, either because velocity regulation is bad, tracking error is bad, the system has encoder errors, interpolating errors. A lot of these secondary effects can come into the laser process and give you something that may appear good, when in reality it could be better because the laser can process the material better with an improved motion system. And we've seen that quite a lot directly. So that's on one hand, and that's a part of this talk, is how sort of these combined attributes of motion requirements that go around transparent media, and they share a lot of common threads, how that goes versus sort of in the alternate case, which I wouldn't want to be too restrictive, is in R&D systems, which PI has a number of leading researchers that we work with in the R&D space, developing new display technologies or new additive manufacturing techniques or combination of these in a really interesting, novel way for what hopefully someday will be a part of our selfies that we're taking in the future. So, so really this goes into branch paths. So those that are working in R&D systems, how do we make that system most flexible that accounts for what's intended today and what would be accounted for what might be done in 5 years, so that you get the most out of your system both now and it grows with the material process as it develops in the future. But one overriding theme that for these two approaches, a very dedicated commercial system and a very flexible, future-looking R&D system, is we kind of start with the laser that'll be used, the beam delivery, what's the intended laser material interaction, what's been looked at to achieve the best desired effect in terms of the material response. And today, this topic is focused specifically on transparent materials. And so really, how do we get that desired effect? It's really by taking the laser and the beam delivery, and now you bring it to PI. Here's sort of the approach and the idea. And now we make it wrapped around a motion system, typically configured around the beam delivery. How we do the motion control and the motion control algorithms, which are really critical, including multi-axis synchronized motion. And while that's happening, how you take that synchronized laser control, assuming the laser has an external shuttering mechanism or pulse picker, and have that work all together, and really to work in some cases directly from a CAD model to a fully fabricated part. And so the laser and the beam delivery is typically something that's incumbent on the groups that we work with. And then all the other parts are things that we work with the groups to give the best, most desirable process. And really, I'll say each part of the process is, I would say, almost equally critical. The wrong laser for the wrong material doesn't work well. The bad or error, badly chosen, or let's say motion with bad characteristics relative to the process will also give you lesser results. So all these things together give the best process results. And what you can see in the lower right-hand corner is a system that we put together. And of course, we started with the laser. We started with the photosensitive mat that you see. And where does that particular material fluoresce or emit when excited by a laser? And then we match those two together. Then we brought in the motion system, the software, and everything that you see here to put on display and show how we synchronize everything to give the desired effect in the material. So really, I talked about the laser and the material and coupling those together, doing applications engineering kind of tests of the type that I did when I started working, and then really trying to mate the process. And a part of that is how fast can the process run. And one thing that we found directly, a lot of this transparent media running with these different ultra-fast lasers that we've been using can typically run fast in hundreds of millimeters per second. So these tend to be fast processes. And they're not always fast processes, but for the most part, fast, high consistency motion is required. And so when we do that, when we step over, what does PI do? And I thought it might be good to show, sort of generally speaking, what PI is doing. You can see in the upper left-hand corner, this is a motion controller that's running all these sophisticated multi-axis synchronized algorithms. A part of our architecture structure is to have an attached laser control module that you can add anytime. It's field upgradable. In some cases, we have lasers that may not have fast shuttering or fast response to an external trigger. In some cases, we've seen even mechanical shutters. And so these kinds of things can sometimes run on the motion controller, but because of this modular approach, if that was to be upgraded, the laser control module can come in and work with pulse pickers and sort of more advanced pulse synchronized motion. And in this case, in the first case that I'll be discussing, this shows like sort of a fixed optics approach with a green wavelength, which is common for what we do. And below that, now you see the configurable motion systems. Scott sort of mentioned this in his presentation, sort of the adoption of our acquisition of ACS and a lot of other work that we've done in, I'll say, the recent past to produce these sophisticated motion systems that really get wrapped and customized to the customer's requirements in terms of beam delivery and inserts and coordinated triggers of what can be done on the laser and the beam delivery and these kinds of things. So this shows some of what we do. Our catalog is pretty broad, and what I'll be talking about are sort of simple cases of processing planar substrates, but this is a part of the core of really what we do to address these kinds of applications. And then down on the bottom, I wanted to show sort of we have a system level machine interface that could really be used to build out a full tool. So once you have the laser and the beam delivery and we sort out the synchronization, we can work with industry standard galvos. This is something that was really a goal of our early development, was to allow the flexibility to adopt industry standards. There's been a lot of work done in galvo technology, and we wanted to leverage that on the software side to make everything work together. So what you see in the lower left is the PI logo as a DXF that's been imported and infilled. What you see on the right is an STL file for an additive kind of process. We've even done subtractive processes, especially with ultra-fast lasers, to do ablation. So this could technically be inverted, and you could be ablating into the material, the PI logo. And then finally at the right, there's a lot of sophisticated multi-axis algorithms that minimize error with adaptive disturbance attenuation. There's really a lot of intelligence. And when I talk about a process result, all of this goes into the process result along with the very base core of the laser material interaction and how those things are creating constant fluence or average power and things like this. So I call this slide looking through the looking glass because from a display technology standpoint, I think a lot of things that may not even have been envisioned 5 years ago, unbreakable glass or completely bendable, flexible displays with true blacks and bright, vibrant colors. It's all these new display technologies that are coming down the pike, and ultra-fast lasers especially are proving especially valuable. into processing these with the best material characteristics. So that really, I'll say that in principle, you don't damage the material, or you don't, by processing, you don't introduce any weakness in the material that then becomes a weakness downstream. For example, in the upper left, this is probably too familiar to most people watching, including me. When you drop your phone, it'll crack and shatter. And the idea is, can we make a display that is basically unbreakable? So you could drop your phone and it's fine. And this goes into flexible displays that we can roll into our pocket and put away and pop out, and they're true blacks and bright colors. And the ability to do that, especially in composites or in chemically strengthened glass and sapphire, is really, the motion system becomes critical to not introduce damage, because you want constant dose characteristics across the material, and the motion can be having following errors, it can be trajectory errors, it can be inconsistent in terms of velocity regulation. So you're going faster, slower, which means the net applied fluence or dose on the material is variable, which is generally bad. You want consistent dose across your structures. So the first example that I wanted to talk about, sort of things we've learned in going through and doing a lot of transparent materials, we'll look first at femtosecond laser cutting of chemically strengthened glass, which has shown a lot of promise for making unbreakable displays, for lack of a better word, and even bendable displays. So now I'm going to play a video to show sort of this approach, what it looks like, and showing a motion system running. Let's run this video. Okay, so this is a fixed beam approach. I'll be talking about a galvo or scanning optics approach. You can see the trajectories running. In this case, we're using V417s, which we use. This is a staged model that you see here doing the motion. This is a line of stages that have debris protection, air purges. They're low moving mass. That's a common term we use in motion, where you don't want to move around a lot of mass because of inertial effects. When you're rounding corners and doing things like that, creating air. And we're using extra large high power linear motors. So the combination of a low moving mass with high power linear motors creates dynamics that are really, to some degree, ideal in applications like this chemically strengthened glass with a fixed beam focus in the glass. So one thing that I don't think is always clear, precision motion isn't intuitive to a lot of people necessarily. And to put it into the scale of kind of human experience, we'll consider it, if the motion system was to follow these rounded rectangles that I've been talking about, and it was scaled to the size of a racetrack, here's what would be the case. The car would only deviate from a perfect path by 3.4 millimeters. So it shows sort of this ability to do dynamic rounding of corners and to minimize error, which can be pretty critical in these applications, and while traveling at 950 miles an hour. So pretty special in terms of what you're getting on the motion side to do this kind of work. So now stepping over, I talked about the V417 in the last slide. This is what we would use for femtosecond glass cutting, running curvilinear or rectilinear motion paths around rounded rectangles. I'll talk a little bit about that and how we deal with that to make these trajectories that are synchronized. But I did want to sort of give kind of a rough bounds of what was required by the application. But maybe most critically, the application could run fast. The laser material process can run quite quick, for lack of a better word, at hundreds of millimeters per second. There's sort of a process depth of layer planarity requirement. You, in some cases, want to be able to run a pulse picker. In some cases, you may not have a pulse picker. But in this case, we can do the pulse picking as well for consistent pulse overlap, even on variable dynamics. And really, maybe one of the big ones to show sort of this idea of, hey, a low, stiff profile, high precision motion system running with a high motor force with low moving mass and a high resolution encoder and all the things that go into building and guiding stages like this, which there's a lot of intelligence baked into this that's unseen. This is what goes into it. And if you look, Newton's first law, the potential acceleration is over anything that's available in commercial roller coasters now. So super high dynamics, high precision, ideal for planarity, a fixed focus running on high trajectories. So this is what we have. In this case, I thought it might be good to show you sort of, you might have a rectangle that comes in, and this is true of a lot of DXFs that aren't laser process optimized. So they come in with sharp corners, and running sharp corners on a precision motion system at high speeds is very hard, just like driving your car around a tight corner. And one thing that happens that you'll see, and this goes into heat affected zone and the use of ultrafast lasers generally, is you can see pulse bunching in corners because you have to accelerate into that corner and you have to accelerate out of that corner. And a sharp 90-degree turn makes that very difficult. And then what you'll get is sort of this pulse bunching, higher dose in the corner, and then your material response isn't what it would be in the places where the pulse overlap is consistent. And so one interesting thing, and this is one of the intelligences baked into multi-axis synchronized trajectories, is coming around a corner and having that corner being rounded by a simple parameter. So from a process standpoint, if you were optimizing this, you would only have one process to try to get the best tight corner with the best characteristics. And now you can see with this corner rounding, slight corner rounding, with this rounding radius specification, you can now see the pulse overlap going consistent. And what's interesting is here, the pulse overlap consistency in this case with this rounded corner is running average velocity. So we can run multi-axis synchronized constant velocity, which relates in this constant dose. This yellow line, this plot here shows two axes running, and it goes from this yellow that you see, which is varying velocity, to now locking on and running extremely constant velocity at the level of sub a single percent to run that constant dose with equal pulse overlap. And while it's doing that, we have an adaptive disturbance attenuating algorithm that's running on that trajectory. The lower image shows without that adaptive disturbance attenuation, and you can see the air as you run around the corners, and maybe this is a good general lesson in precision motion around tight corners. The air starts to spike, and then you have your regular sort of steady, what I would describe as steady state air, and the adaptive disturbance attenuating algorithm that's proprietary to PI is now showing these air characteristics dramatically improved. Now, maybe you could live with a little bit of higher air in the process, but that also means that you can turn up the dynamics to run faster, especially in this case, because now the adaptive disturbance attenuation creates an air level at a higher dynamics that you might find at lower dynamics. And that goes into creating a process that supports, high throughput, for lack of a better word in this case. So the next one, and this goes into the topic of selfies, are camera covers. Camera covers are typically made of sapphire, and sapphire has been processed by a number of different lasers, nanosecond, picosecond, femtosecond. This particular case was a little bit more open-ended by a process knowledge or an established process. So I'm going to show sort of how this one is using a galvo and how we work with galvos. So I talked about galvos as sort of this industrial standard we wanted it to work with. This is what a galvo does. So you can see the circular trajectory, you can see the stages working with the galvo, but the galvo is taking care of the synchronized motion scanning with the laser. And you can see galvos can enable really fast processes with lots of tight corners with dense structures. So generally speaking, the idea is if you have compacted, highly dense kind of structures, running a galvo typically yields better process economics than just running stages alone and potential. But galvo, that's data lens, and the galvo has a fixed field length that's a trade-off with resolution. So the stages will give you a broader process field relative to what a galvo can do alone. And that's a part of the idea behind this. That if you had a big substrate with lots of things that needed processing, get the galvo to run it and then have the stages open up your depth of field without compromising resolution. So galvo plus motion, what do? We have a system interface, and this goes into sort of maybe a fundamental difference with the last one. We had a rounded rectangle, and the rectangle is not a dense design. It's just four lines, for lack of a better word, with curled corners. In this case, you might have many compacted circles on a single substrate or something like this that might be more typical of running a sapphire process, or at least one sapphire process. And so in this case, many rounded rectangles, many features, like what you saw in the previous slide, a galvo tends to be a better approach because you can run around the corner scanning a beam. You're not technically moving any mass. So that tends to be faster with dead structures, and there becomes a trade-off there for resolution too. But why sapphire? Sapphire is hard. It's scratch resistant, so you see it in mobile devices for what you're wearing. Yeah, and on the backs of camera screens are as camera covers. And to process, in this case, the idea was to have a fast-moving, high-throughput process with a galvo that had to be coupled with sort of not V417 stages, so we have a lower precision, equally dynamic but lower precision version called the V817, and the idea is that this would be used for highly dynamic, more looser error tolerances at a lower price point. And so that's sort of what we had here. The idea was in this particular case, there's never the intention to work in really super high precision, just precision. Everything PI does is precision. And there's more forgiveness in the process itself, but still how to work with DXF, how to work with STL, a picosecond laser, and analog power control and things like this. So now the software and the stages were detuned. So still the software is parsing tasks to the galvo on the stages in a synchronous way direct from model. And then there was the desire to have a complete motion system that's taken out of a crate with software to now build in the optics and do the process. And so the result was this. We used ScanHead from ScanLab, Exceloscan. We ran, of course, the motor force dynamics of what I was talking about. The 817 is actually slightly higher dynamics in an unloaded state. And now you have your software that can run and parse the individual tasks. And the granite, of course, gets customized to the working distance of the S-theta optics and the galvo ScanHead, and the path is designed in to work from the customer appropriately. And again, we're using sort of these high dynamic stages that are really ideal for these two processes. So finally, the last example is going to be on PT and sort of flexible display technologies with composites. This will be kind of a quick one. It shares a lot of commonality with chemically strengthened glass cutting. Only now there's some extra potential for melting or doing damage to composite layers with a single laser. That can be quite challenging. So now even the tighter constraints that might come around femtosecond sort of cutting now get boosted even more, because when you have a composite layer that's being processed with potentially with a single wavelength or a single laser characteristic, you don't want to damage any of the composite layer. And so everything gets tighter. There's some cases where from a process standpoint, you might want to use an assist gas. Of course, it's preferable because of cost to have no assist gas. Fume extraction, so you're not taking any of these particles, breathing in any of these particles. And again, tight radii of curvature, fast processes, narrow process window, process depth of layer, especially in a composite, could become critical. And we've seen that this can get into very large dimensions. So it really could be a fixed approach where you have a flat substrate flying over depending on the beam delivery, or it could be really one of these integrated XYs that you might see here that are running good process planarity in an air bearing. On the left is an air bearing, on the right you'll see mechanical bearings. PI does both. It's one of our core excellences. So in a system like this, there might be some flexibility, and I'll circle back around to my R&D. In an R&D way, researchers may not know where the road will lead ultimately and what they want to do, and then it's building in maybe this higher level of precision through air bearings and things like this, where you don't have that kind of problem, or where you can grow into more bigger processes faster with tighter tolerances. So that'll come to the end of my talk. You can see our wall of patents for all the innovative technologies that PI has come up with over time.
All right, thank you very much, Scott and Matt. And we're gonna take a couple of questions. I know that we're getting to the end of the hour, but if you wanna go ahead and ask your question now, we will follow up with you later. Also, if you think of a question after the fact, you can email us at webinar@photonics.com. and we will get back to you. So, Scott and Matt, my first question for you is how much time would it take to get a photonics alignment system with the capabilities you described up and running? And what support is available during and after the setup phase?
Well, as in many things in life, it depends. It depends on the devices. It really depends on the fixturing. Things such as gripping and the accommodating the shape of the package, non-trivial. In fact, the alignment is the easy part, really. Typically, if you have some experience or if you are working with one of our partners, you will find that it is possible to get the basic process working in hours or days. But the fixturing, the bolting things together, arranging for the pick and place and various metrology needs, these are things that can take some thought and take some time and take some expertise. So this is where the people like Form Factor and Tegema are providing a real service, because it's easy to underestimate some of that physical fixturing relationship thing. For example, making a wafer prober. You might say, well, I'll get a couple of PI systems and bolt them on top of a wafer prober that I already have. And that is something that many of our customers have done, and many of them have been successful at it. But note the assumptions. The assumptions are that the wafer prober that you are retrofitting is stable enough and that the structure is stiff enough that all of these nanoscale processes, very fast, high dynamic nanoscale processes, can proceed. If the wafer prober is of low quality, or if it's old and it vibrates, electrical testing won't care. Photonic testing will. So it depends. It depends on the circumstances. It depends on the devices, and it depends on, more than anything, the fixturing.
All right, thank you. Matt, would you like to add anything?
The only other thing that I might add in addition is sort of PI provides open source software and examples in Python and in LabVIEW. So I think to some degree there's also an easier adoption because there's an open source software to sort of start from.
All right.
That's a very good point. Yeah.
Thank you both. My second question, how complicated is the tuning of the hexapod controller?
I can take that one.
Go ahead.
I've been with PI for 24 years. I've never had to tune a hexapod. They come pre-tuned, and so they're really easy to tune because you don't have to tune them. So I hope that that's a good answer.
What is the typical standard deviation of equally spaced laser pulses from your controller?
Yeah, that's a good question, and it really, I would say it's a little bit dependent on conditions. We have fixed distance sort of compensation on variable dynamics, so your pulse spacing is equal. We've done a lot of studies on that. The number that sort of comes to my head, depending on the condition, we found it gets down into nanoseconds. So there's nanosecond level variation. So really, we found, at least in this fixed pulse distance, even if you have a very high precision system, the dominant error mode is going to be the tracking error as you're moving, not the timing or triggering error that's coming from the high performance fixed distance laser control module as an example. So yeah, it's a little bit variable, but it's really high performance, for lack of a better word.
All right, thank you. Can you explain again the trigger options of the laser from the controller?
Sure, yeah. So typically we send an external motion synchronized trigger signal in a few different ways. The most basic is we have a digital output that's synchronized with the trajectory. That's on every controller. That runs at typically 5 kilohertz. So that's how quickly it updates. If that isn't necessarily sufficient, then we switch over to a laser control module, which can run up to 10 megahertz. So it's a much faster, but it really depends on the process. So we have both options available. We go with this simpler, lower cost option when we can, and then if we need to, we go to LCM. LCM is still, I think, a great value, but then we'll go to an LCM should we need to.
All right, thank you. I've got a couple more questions. Can you elaborate on the differences to other available automated alignment solutions?
Okay, yes. The thing that is unique about the PI implementation is the ability to perform multiple alignments simultaneously in parallel. That is where the big time savings, the 99% time savings comes from. Nobody else has figured that out yet. There are alignment technologies that were introduced in the late 1990s. I was involved in some of them. They're still being used, but they're in today's applications with multi-channel devices. They're just so much slower. So the speed, the throughput, the productivity, these are where our technology is a real step forward for the industry.
All right, thank you. I'm going to take one more. Are all of your laser stages based on linear motors?
Yeah, and that's another good question. I'll take that. In most cases, we prefer a linear motor, or what might be described as direct drive stages, because of the trajectory characteristics and the consistency of motion, for lack of a better word. So everything is running smooth with the equal rate, synchronized with minimal trajectory error. In some cases, we may go to a screw-driven stage solution, but it tends to be secondary, and if the tolerances are pretty loose and the conditions are amenable to it. But by default, we tend to go linear motors.
All right, thank you both for answering all those questions. I'm going to end on, it's not a question, but I'm seeing a thank you note, so I'm going to pass that along. And I just want to reiterate that if you think of a question later, you can always email us at webinar@photonics.com, which is webinar@photonics.com. As well, if you'd like a PDF of the slides from today's presentation, you can email us about that too. And again, this whole session was recorded. It will be online in a couple of days at the most, and you're going to get a link to that in your inbox. So I'd like to thank our presenters one more time, Scott Jordan, Head of Photonics for PI, and Matt Price, Technical Manager for PI, and everybody here. Thanks for participating in improving production economics in photonics test and assembly and ultra-fast laser materials processing of transparent materials. This is presented by PI and hosted by Photonics Media. Thanks, everybody.
Thank you.
Thank you, Sarah.